The next two sections that we're going to get into are around critical capabilities, right? These are the features that you need to run in order to be successful and to basically succeed in the hybrid and multi-cloud world that we live in. And a lot of these features are going to sound familiar to you, but the nuance and the twists and the subtleties of them in a hybrid and multi-cloud world are going to be the things that we focus on. So we're going to start this first section, which is called Kubernetes Multi-Tenancy and GUIs, and we're going to dive into that, and then the next section beyond that we'll get into right after the demonstration. So let's talk about Kubernetes, right? So Kubernetes is the most powerful force in the cloud today, right? And we've invested heavily here, and it's paid off with extraordinary dividends. But what made it so powerful, right? What are the things that drove this? So first of all, it transmitted billions of dollars of IP basically to the rest of the world from a cloud computing infrastructure framework on how you do things. So a startup in Singapore could learn the scaling secrets of Google, right? A system administrator or a system integrator in Austria could learn the automation secrets of Amazon. All of these things became available to the market. And that was a function of the fact that you had one abstraction layer that just worked better, right, across public, private, and edge. And it's just simply better at managing compute resources. It allows you to drive scalability. It allows you to ensure continuity and resilience. And it just worked better, right? And that API just worked better. And I think the last thing that made it such a powerful force is that it was open source. And so it was so easily adopted. The friction was very, very low for adoption. And more importantly, it developed a very, very robust ecosystem around it. And a very lucrative one, which allowed it to really blossom and grow into what it is today. I'd say that Kubernetes has the scale that AI could only dream of, and I think that's a function of just going to look at any one of those CNCF eye charts at this point. It is a very robust community with lots of successful companies and a lot of companies that they're betting on success as well. Now, Kubernetes has a favorite object storage. A favorite storage type, and that favorite storage type is object. The file and block folks will probably argue that point, but truth of the matter is their legacy at this point when it comes to the cloud, right? And the reason for that is that, Kubernetes wants RESTful APIs. And guess what? POSIX is in a RESTful API, right? Object storage is built on RESTful APIs. And so it's too chatty. It doesn't scale particularly well. And so it really has fallen really into the backwater of technology. And that's a function of the fact that at the end of the day, you can't run it at the scale that you want to. Scale is a huge part of that, right? Kubernetes is about building large-scale infrastructure. And so object storage is particularly qualified to move from GBs to PBs, right? It is the most scalable of all the storage types. And properly architected systems can be the framework for Kubeflow, for AI/ML, for large-scale smart stores, for any number of things that require sort of active data analysis, yet scale at the same time. We like to call it performance at scale, but it's a really important part. And then finally, Kubernetes is modern, and it looks for modern endpoints and modern other services to talk to. And so that's where, again, object storage shines. From erasure coding to the S3 select, which is the predicate pushdown, you have a storage system that's built for the modern cloud ecosystem. That, coupled with the performance that we're able to drive today, really makes it a very, very different story than it was even 5 years ago. And despite decades of evolution, file and block simply don't offer these types of answers. And no amount of connectors or integrations is going to get you past that. Yes.
Now, quickly, I follow you up to a certain point. If I have to run a database, I don't use object storage. And there are several reasons for that. Well, the first one probably is that there are no databases that run on object storage. So if I need Postgres or MySQL or MongoDB or whatever you like, it's difficult to have an object storage interface to make them work. So I agree that for many workloads, object storage is a good option, but there are actually, it's not the primary storage. It's one of the many options.
that statement is actually itself is looking backwards, right? Here's what is actually happening. Look at every modern database in today's world, right? Particularly the ones that need to reach scale, right? Whether it is Snowflake, like BigQuery, all the way to Power BI, Azure ML. Look at those stacks, right? Then look at Kafka, which is from Confluent, Elasticsearch. Every one of these, like even Splunk is kind of a log database. Every one of these modern systems that need to scale, they are now either they started off on object storage, or they eventually realize that they need to have object storage for persistence. And every modern database that has scaled is actually built on object storage, or they transition to object storage. And there are still some databases, the ones that actually transitioned. For example, if you look at unlike Snowflake, which is pure S3 object storage underneath. If you look at Splunk, for example, like Splunk, Elasticsearch, Kafka type databases, they are all data stores, different types of databases, all the way to graph databases.
No, I agree with you on this, but actually, all the indexes, many, especially relational databases, are not object stores. I mean, I tend to agree that if you have a very large repository and you want to, to store data in that, it's okay. But probably all the indexes and everything is out of the object store. I mean, so it's part of a larger solution anyway. It's not it's primary in terms of capacity, but probably not, even if I think about the protocol S3, this is lower than any object storage, block storage that we can have today. So if I have to store, a key value store, even if object store sounds perfect in theory because, we are a similar concept, it's probably faster. I mean, to have it on actually we are moving on in-memory databases. So we need absolute performance, and object storage is not designed primarily for that kind of performance.
Yeah, so if you see the object storage play is actually throughput play, not IOPS play, right? And then if you want to do mutations and indexing, object storage is not the place to do it, right? Then how do you do transactional database? OLAP databases are anything from key value store, log store, anything message queue, they all figured it out how to do it, but let's say purely from a transactional database point of view. Actually some of the innovations that are happening today in the market, this is actually a couple of years before I noticed Intel and Facebook did this work. They took MySQL InnoDB backend and replaced it with a ROX cloud database. What they did was the SS tables, table segments went to object storage, and I asked them then, where would you store the memory index? They said that went to Kafka. So they actually built a transactional stateless database on top of MinIO. And but then I would say, well, that one, even I myself probably won't be comfortable, at least for today, to put it in production. But the move that the transactional databases are also going towards is the indexing part. First, if you look at the object storage part, object storage, use it for persistence and throughput. The table segments, even in a transactional database, are like 2 MB extents, right? You pull them out, you do all the mutation in the local memory. When you are ready to commit the transaction, push it back. But the mutations should not happen across the network over 4K or 512 bytes. That's too chatty, doesn't scale. And on top of that, the local memory is the fastest one. So they are actually, their move, I would say, will happen towards the persistent memory. Today, the DRAM is pretty fast, but you could lose the transaction and not roll back. There is already a move in the transactional data stores, the smaller transactional data stores. The scale-out transactional databases are also moving, like Yugabyte to everybody is moving towards object storage. These are OLTP transactional ones. But if you see for whatever they are persisting today, they use local drive, replicated, they take care of replication and it's high availability. Every modern database, if you look at Yugabyte, for example, right, or CockroachDB, they would not tell I need SAN. The traditional databases will tell I have to have SAN or NAS. There was always an argument which SAN is better, but in today's world, every OLTP database have gone scale out. And when they go scale out, they don't use SAN. They actually use local JBOD or JBoss, and NVMe drives are perfect fit for that. I would say Optane type persistent memory would actually push them to next level. So the block storage, we are not talking about file and block, but local block storage for immediate persistence.
No, yes, I don't argue, but it's block storage. I mean, logically speaking, is a block device for these databases.
We are in agreement then. So the block storage, end of the day, CPU, network, and drive, you have to talk to them. Even MinIO needs block storage underneath. The question is really about local block store, which is just local bunch of JBods or JBoff versus SAN and NAS. SAN and NAS protocols are the network block storage versus local block storage is really where the transition is going. And the local block store, every modern database is going towards local block store and distributed, replicated, or erasure coded. The network block store, SAN and NAS, are kind of going away. They are considered legacy in the modern world. Probably the EBS type block storage, there is play because there is still some applications not purely cloud native and stateless. They would actually require a block storage, but the primary storage in the public cloud today is not file and block, it's object storage. So Kubernetes has adopted that, Kubernetes became the compute standard, API standard for infrastructure, but then the applications coming from modeling themselves after the public cloud, they are all seeing that public cloud object storage is the standard, and that's the same standard that they will adopt over containers and Kubernetes as well. So that's where this trend is coming from.
So how do you position yourself versus competitors like OpenShift Container Storage running on OpenShift that provide all three of those capabilities instead of just one? What do you say to that?
Yeah. So it's actually my previous project Gluster, when S3 started picking up around 2008, it became very clear that S3 would succeed. And what I did back then was I added S3 API to Gluster. In fact, I added Swift API as well. And that way, my argument back then was, hey, you can actually do file, block, object all in same system. Ceph attempted that, and few others are in similar play, right? But as soon as I added the object API, I understood that the very essence of the object API, if you look at Amazon S3 is not built on top of EBS. In fact, if you want to protect your EBS, Amazon will tell you snapshot it to S3. And the real advantage of S3 is actually about dropping the legacy POSIX semantics. Once you drop all the legacy requirements, Object API is about just atomic immutable blob API. It's just a REST API. It's really a web service for accessing data. That's actually a much simpler problem. I understood that adding S3 API to Gluster FS, that I can be a decent file system, but I will never be a decent object storage. Putting both together, I'm carrying all the POSIX baggage along with me, and I would never build a better object storage if someone else went back to the drawing board and came back with an object-only system. And if they told me that if a customer wants only object storage, they're going to pick that over me, I wouldn't have an argument there. It was a revelation for me trying to do that. I understood that if I try to do all three, file, block, and object are actually three different products. They are three different architecture. There may be some commonalities in terms of metadata architecture or consensus protocol and stuff like that, but they are just like database is different from SAN. They are actually three different products. Trying to do all in one will result in a Swiss Army knife type product, and that would be the very weakness of the system. It's also the reason why you saw Ceph-like products never took off. It's so heavy, so complicated, and they couldn't beat file system they are not the best of the breed file system, best of the breed block storage or object storage. For us, the goal from day one was we have to beat Amazon S3. If I'm going to carry POSIX file and block legacy along with me, I would never stand up against Amazon. I would be a tiny minority player. That turned out to be right for us.
So what do you say to Kubernetes customers that come to you and say, your object storage is great, but I have a more diverse set of storage requirements? What do you advise that they conform and start to utilize storage in the way that you're recommending, or what is the overall holistic answer for those types of customers then?
So we always tell the customers that, like, if you want block file, then they ask us all the time, right? Even very early on, I told you that we would not do that. And we told the customers always that if you want NAS or if you want SAN, like go NAS, go to NetApp, SAN, go to EMC or Pure. They are the best in that category. And even if I try to build one, I would be lying to you that I am better than them. That if you want NAS, pick the best of NAS vendor. If you want SAN, pick the best of the SAN vendor. If you try to get all three from one and one unified product, it is not going to be better. You will end up getting a Swarmy knife.
So, Anand, if I can say one thing, I think what we've been hearing, I mean, we've been going on for a moment now talking about the supposed, let's say, merits of object storage and future architectures and so on. But when you go to a customer, and they have a problem they need to solve now. So you're probably not going to tell them that they need to refactor all of their databases and core business applications to run on object storage, right? I do get that you do object storage and that you advocate for it. But what would be I would say, can you highlight some of the use cases which you're really seeing today in the enterprise? Not hypothetical stuff, but cases where people do, cloud native workloads, they need to use MinIO.
That's actually a very, very, very good question. So we struggled with that for quite some time in the beginning, and but then we were stubborn and we were focused, and it helped us overcome this issue. So here, the problem, if you see, right, like say previous generation, when bare metal to virtualization happened, it was a smooth transition. You didn't have to rewrite your application. You could just go virtualize and consolidate your infrastructure without any changes to the application code. But that's not what Amazon pulled off in the market. Amazon's whole idea was, I will give you productivity, everything through API, pure awesomeness for developers, but then you have to leave all your legacy stuff behind. You have to rewrite your application. To be cloud native, you have to start. You have to start from scratch. The cloud native world and the enterprise world are actually incompatible with each other. They do not mix. Even if you try to retrofit your legacy applications into the cloud, it would actually cost you more, it wouldn't scale, and it's going to be more difficult than running your traditional file block VM type workload. And this is basically the fact, right? And so we had to make a choice very early on that the only way you can do a good job here is you have to learn to say no. We basically for the market, enterprise market was like, I want public cloud to look like private cloud, not public cloud to look actually the private cloud to look like public cloud, not the other way around. We targeted that market. The applications that were cloud native, they were ready to adopt object storage because they were built for object storage. They were born in the cloud, and we targeted that market, and we left the traditional file block VM type world. And over the last 5 years, the industry went through a significant transition. It grew at such an accelerated pace. Today, what we are seeing, applications are cloud native. The very weakness of MinIO, that is object storage and S3 API, the enterprise applications could not take advantage of object storage because they spoke file API, and we learned to say no. But now enterprises are finding applications are written for S3 API, and they can't speak file API anymore, and they couldn't use it on NAS. So the very weakness became strength. Today, you look around even the traditional ones, whether it's Teradata Vantage or even Greenplum, like one of the oldest ones, right? Vertica Eon Mode, Splunk Smart Store. These are powerful enterprise applications from the old universe. They speak S3 API. They don't even speak HDFS API. And even Teradata Vantage has to use MinIO HDFS gateway to talk to HDFS. Now we are seeing that there are two big ecosystem came towards us. Those basically, if you go into every organization, there are three silos we noticed. One was the enterprise IT, well understood, right? In that world, you couldn't touch it. The applications were basically file block and VM. We left them aside. Then we saw the data teams. The data teams basically are the data infrastructure. traditionally came from DBA world and they ran the data analytics and data infrastructure. They even moved to Hadoop and then learned the hard way that HDFS is not what they wanted. And they saw the cloud and they realized that instead of Yarn and MapReduce data locality, they moved from HDFS to object storage, data pipelines, Kubernetes, AML, Kubeflow, model it after the public cloud, and they came to Kubernetes as well. That was an easy win for us. They needed scale, they needed performance, AML. Every modern application could be something like Snap or Twitter or Uber or powerful enterprise applications. Look at them, right? Their application code is a single page, tiny app. It's an app. It's a tiny application. What is bulk of their infrastructure? It's basically dealing with the data. They are crunching the data, analyzing it, and then feeding it back to the application. Application makes decision based on the data. Bulk of every modern application is basically machine-generated data, log data like JSON or CSV type data. They're constantly capturing, or it could be text. They're constantly analyzing that. That data previously went to database and then came to object storage, came to HDFS. Now they're all straight coming to object storage. That's a clear, easy win, easy case to make. The AML, analytics databases coming from HDFS world to object storage. The other one was always our sweet spot, was cloud native applications, born in the cloud, containerized applications, every modern popular programming languages. In fact, if you talk to these developers, they would be like, what is your first app? And then even if you tell them that's where you have to preserve your mount command, so you have to make an entry, then they'll be, I can't edit that file. Then you have to tell them you have to be root. Why should I be root? They're like, can I do pip install or npm, like get an SDK and start writing my code? You can't even explain to them about POSIX. They come from a very different world. The cloud native applications, data infrastructure, data analytics, these two were very strong play. We got that part of the market. The enterprise finally is waking up because VMware is also saying that now the future looks like AWS and we will give you AWS-like infrastructure. When VMware is saying that, finally the IT is waking up to it. That transition, I think it will take like another 5 years, but we are ready for the data as well as cloud native applications.
Okay, so what is it about MinIO that makes you so good at doing object?
So it is really the understanding. What's that, Jonathan?
I said, funny he should mention that. Why don't you take us through this slide, AB?
Yes, it's actually a very important question, right? I wouldn't have done that. Actually, after doing Gluster, I was pretty clear. First of all, I was not going to do another startup. And the last of it is going to be another storage startup, right? And in fact, when Red Hat asked for, like in any M&A, you do this non-compete agreement, right? I told I can sign on a blank check, a blank agreement. I'm not going to do another startup. Don't worry about it, right? And you can imagine, I didn't want to do this. But the reason I came back to object storage was I saw a simple problem compounding and growing at an unprecedented rate. And this was not about storage, it was about data. And object storage was more closer to a data store than a traditional file system inside the kernel. And what I saw was the problem was very different and very simple. Everyone was trying to find complex solution to a simple problem, and I saw that it demanded a simple solution. If you look at the very heart of S3 API, is simply a REST API, and every operation is atomic and immutable. Compared to a file system or a block storage, you have to deal with 4K or even smaller blocks, and 512 bytes or 4K blocks. And file system is even more notorious because unlike block storage, which gives you exclusive access to a LUN, in a file system, it is anyone can open the file and mutate and chat. Even the locking advice, most of them were just doing advisory locking. It's very hard to achieve concurrency right without sacrificing performance. NFS, in spite of decades of maturity, is riddled with holes, and it's very hard to get it right because the last thing you want is to lose data. Even an occasional corruption can kill the company, and I struggled with that problem when I did Gluster, right? But when I saw object storage, it was actually, this is where Amazon, I give all the credit to Amazon, that It is simply you can't make a change to an object within its content. You can't make byte level changes. You can't mutate. Every mutation is a new version, which means that it's simply a web service with REST APIs. You could essentially write an object storage in PHP language, and application wouldn't notice any difference. It's a very simple problem. If you look at the MinIO design, it's reflected very much in its design. MinIO server is actually a web server. And the entire functionality is simply functions stacked up as web handlers. Whether it's erasure code, bitrot, encryption, they are simply functions written in Go routines and just simply stacked upon each other. You crash a system in the middle of busy workload, you wouldn't lose a single transaction, because every operation, when you do say put object, all I'm doing is I'm doing erasure code, encryption, all these operations are performed. Now I have tiny blobs of data, I scatter and commit to the drives. It's actually that simplicity of storage is these storage functions are just web handlers attached to a web server, and everybody else, what they thought, I can take my distributed file system design that already takes care of replication or erasure code, and then they looked at S3 as just a S3 API proxy. They looked at S3 as just a proxy problem. We looked at the storage as entire storage is just a web handler to a web server. And for them, they look at it the inverse way. Philosophically, it's like we try to find simple solution to complex problem. They try to find complex solution to simple problem. That is where MinIO got its strength. I saw that whenever the market is trying to build complex problems and they can't think like us, it's a cultural difference. Everything we did is out in the open. They still cannot copy MinIO because they can't think like us. It's very much like it's one chef to another chef. They can't exchange recipes because of mental block and ego, right? So it turns out to be an advantage for us.
So I think to summarize what AP just did much more articulately than I could is that, we were built for this. It's in our DNA, and I think the DNA piece is very important. Our focus, which we've talked about over the last sort of 20 minutes, is critically important. The fact that we only do one thing because we're building a best-in-class object store here. And that's resulted in the fact that between our Kubernetes nativeness, our S3 compatibility, has led us to a position where 62% of all our instances are containerized and 43% of those are managed using Kubernetes. That's among the highest penetration of those two stats that you're going to find anywhere in the industry. And it speaks to the fact that this is our native state, and this is what we shine and this is what we do best. And so we're really well positioned for this concept of the cloud, which is a multi-cloud and the hybrid cloud, not some fraction thereof. So we're going to switch to another topic here because this is one, again, that you probably have heard. There's going to be obviously some debate around this as well. But AB, why don't you take us through the importance and the nuances between multi-user and multi-tenancy as it applies to modern cloud architectures?
This is one area the storage vendors are beginning to realize that they have to go back to the drawing board to really be cloud native, because historically, multi-tenancy for them meant just multi-user. In a single system, you basically partition the users based on users, groups, roles, policies, and you could just accommodate multiple tenants in the same system. But that works for a small scale. But once you come into the cloud native architecture, everything falls apart. And on top of that, you are also fighting Kubernetes because you are now doing your own orchestration, your own isolation, which you really cannot do as effective as Kubernetes. And also you can't give the familiarity to the Kubernetes world. The traditional storage vendors who came from the appliance world, or even the bare metal software defined vendors, all they did was they took that, put it in a container, and they said, we run on Kubernetes, or we wrote some CSI drivers, and we are now Kubernetes ready. That's actually not the case at all, right? When it comes to the multi-tenancy, that's where you will see the true difference when it comes to the cloud native architecture. It is Kubernetes should do the job of isolation, orchestration, and scaling of these tenants. Every tenant here, a tenant could mean just different customers. Say you are box.com and you have different customers fully isolated in their own Kubernetes namespace, or it could be same same customer, but multiple applications. Or it could even be the same application, test, dev, staging, prod, developers have their own instances. Everything is basically a tenant is kind of an Kubernetes. In Kubernetes world, it's a namespace. Every time you say, I want to upgrade the staging one, I want to test the scaling one, scaling on the staging cluster, you should do the Kubernetes way. It is Kubernetes should do the orchestration, isolation of these tenants.
AB.
Yes.
So in the multi-tenant space with multiple namespaces, is each of those an isolated storage? I'm not even sure bucket or how's it separated? How does it separate the storage behind all this? I guess is the question.
Yeah, so it's an important question too. That there is a lot of details there, and Kubernetes job, like if you look at the ESX for VMware. ESX job would be to virtualize physical to virtual. Whether it is CPU, network, or drive, it is the job of the ESX to virtualize that, right? Similarly, in Kubernetes, the application should not be dealing, say MinIO itself is running on a container. We shouldn't be touching the bare metal. That's the job of Kubernetes abstraction. Kubernetes abstracts the physical layer to the container layer. So the drive, network, and CPU, now specifically on the drive is where the CSI layer comes. So the CSI layer, in fact, all modern data stores, what they are looking for is a local PV in Kubernetes terms. It's a local persistent volume. In bare metal terms, the equivalent one would be called JBOD or JBOF or just local drive, right? And Kubernetes has abstracted that layer. Whether it is a local drive or a network drive, they are just persistent volumes. The job is its persistence, but they all appear as volumes. Technically, from application point of view, you wouldn't notice the difference whether it is a local drive or a network drive. Sure, you can ask for a shared drive or a non-shared drive in Kubernetes terms, right? Now, from MinIO's point of view, to answer the main question, when multiple tenants are running, say I bought myself a 10 petabyte cluster, and say these are 16 node dense JBOF cluster, and now I want Kubernetes to manage all of the physical layer. Whenever I provision, say Ray asked for a 4 petabyte cluster. Now I have a 20 TB cluster. They all can be just different clusters, different MinIO instances sharing the same physical infrastructure. But when I would put my developer instance for 20 TB, Kubernetes will say, okay, I have these 4 nodes. I'm going to carve out 20 TB for you and give it to you. But 4 petabyte across the 16 nodes, I'm going to carve out that much. The provisioning part is Kubernetes' job. The Kubernetes, basically the CSI layer. Here is where MinIO has something called direct CSI. Direct CSI is basically a persistent local volume manager. Like OpenEBS has local PV, VMware World, they actually introduced vSAN Direct. Increasingly, the move for all data stores is not just for MinIO, whether you are running Cassandra or Postgres, like pretty much all the databases are also moving towards the local PVs, particularly the distributed databases, because they handle replication durability just like MinIO. But Kubernetes plays the role of taking those machines, say I have these 10 petabyte hardware, I'm going to run multiple tenants on the same hardware, but Kubernetes does the job of who gets how much space. In fact, there is a bigger case, like say Seagate has multiple racks, 100 petabyte cluster, but any given time, one tenant will only ask for, I want 40 TB, I want 200 TB, I want 3 petabytes. When that happens, they spin up, say I would spin up, MinIO operator would spin up a 3 petabyte MinIO cluster, but there is hundreds of petabytes of physical drive space, right? MinIO, at the time of provisioning the tenant, MinIO will make a claim to the Kubernetes CSI layer, which is the direct CSI in MinIO's case. Then the CSI layer will see, aha, I have these nodes out of those 16 racks. I found these 4 racks good for you, or even across 16 racks, I picked the right nodes that are appropriate for you. So as you provision more and more tenants, Kubernetes should be the one finding these nodes are already busy for these tenants, don't touch it. These nodes are underutilized. Kubernetes should be doing the resource management isolation. If I'm fighting it, if I'm doing it all by myself as a single monolithic piece, this wouldn't happen because now I'm not utilizing Kubernetes. I'm not really cloud native. You're following me?
Yeah. So behind this multi-100 petabyte cluster rack environment, I'm carving out, petabytes or terabytes or whatever that are in this namespace are typically, they're owned by that namespace, and only that namespace has access to that backend storage. Although MinIO is controlling all of it, the whole major cluster.
Exactly. Why is this isolation important? Other than it provides you as a DevOps, you are now using Kubernetes to do the orchestration isolation. Everything, like say you apply these, say this tenant is a free tier. I don't want them to use more than 2 CPUs per core. You want to control them, all that. You are familiar with the Kubernetes way of everything. Like in the container, I say this tenants, all containers, here is the SLA, here is how much CPU memory I can use. You are now managing MinIO, no different from any other web application running on Kubernetes. And this is a very familiar way to manage your infrastructure, not MinIO proprietary way. But there are bigger things to this requirement. The real bigger requirement is that if I want to say in almost all these cloud native environment, you will run into this problem that even if it is same tenant, but testing, staging, and prod type, or it's multiple tenants, say this particular instance is running a core banking application. It's approved by InfoSec team. Only upgrade with InfoSec team approval. Only there are critical security vulnerabilities or bugs. Only then you have to do. But even that you have to get InfoSec approval. But a new application, new project, they want a new feature. Can I run multiple different versions of MinIO on the same physical infrastructure? Yes, it's an important requirement. If you put all the eggs in one basket, a multi-user type traditional monolithic design, even though they are scale-out distributed architecture, if you simply did a multi-user based multi-tenancy, you're not using Kubernetes model, try upgrading the cluster for a new feature, you just broke everybody else in the system. Large downtimes, planned migration, those days are gone in a modern cloud native world. Modern cloud native world is every patch I'm writing today in my application, I want to spin up a MinIO cluster and then test it out. If it did not see any bug, I'm going to commit my code into staging. Staging did its own series of tests. And within hours, I would expect that my code to go to production. They are doing multiple times multiple times a day. They roll out the code to production. If they cannot be this productive, all bets are off. These are critical requirements in a cloud native environment. You can't really do this the old school way.
So question here, we still haven't talked much about the architecture of the product. So what is the relationship between the MinIO cluster and the Kubernetes clusters that you are providing storage to? Is that a one-to-one mapping? Is that deployed only within the Kubernetes cluster itself that it consumes the storage? Is there a multiple-to-one mapping? How does that work?
So let's take a simple case, like say I have 4 servers and 16 drives each. So you have 64 drives, right? Now, that's the physical cluster, 64 drives. Say 64 1 TB NVMe drives, I have 64 TB capacity to keep the math simple. Now, you can, when you spin up MinIO, you say you want to spin up a MinIO tenant and you say, I want all 64 TB to be given to a single tenant. I would simply make a claim, I'll spin up 4 pods and each pod will make a claim for 16 1 TB volume, right? And now essentially Kubernetes will spin up a MinIO tenant, and that is a tenant basically is the namespace, right? There are 4 pods, 1 per physical host, and each host will actually make a claim for 16 1 TB volume. So essentially, I consumed all of the 64 1 TB drives in a single cluster. From a MinIO client application point of view, it will just look to you as if it's one single large MinIO namespace. You won't even know these 64 drives.
No, but is the MinIO service co-located on Kubernetes workers that are themselves contributing compute to Kubernetes pods? How does that work? Are my compute workers separate from my storage nodes, or is that co-located within the same cluster? We still need to understand what that architecture looks like.
Yeah. So from MinIO point of view, it doesn't really matter if you have 3 CPU cycles, 3 CPU cores. Your applications can coexist. On a smaller scale, typically you would do the HCI route, like a hyperconverged type route. My compute nodes also have drives in them, and I'm just going to run MinIO cluster and my applications along the side, and they are just different parts. And Kubernetes basically has all of them co-located. And but as you scale, what we almost always find is as they scale, the compute needs and the data storage needs scale at a different pace. I was actually quite surprised when I started seeing these larger deployments. Even some of these who came from the Hadoop world, I would assume that the compute to storage ratio will be like 4 times at least more compute than storage nodes. Storage nodes tend to be denser and compute nodes tend to be thin and more scale out. I was surprised that the Hadoop guys were complaining that, no, my data is growing faster than compute, and Hadoop doesn't let me have like more than 100 TB type drives. A lot of my compute nodes are idle. Almost all the scalable ones, what they do disaggregation of storage and compute. But from Kubernetes point of view, they are all basically a one Kubernetes namespace. When MinIO is provisioned, we get the affinity because we are making the claim. MinIO will automatically get provisioned on the nodes that happen to have drives attached, but the compute applications can go anywhere. But as they scale, the compute applications, because they are stateless, they would go on the compute nodes. Often they're just annotated. Those parts are annotated to go towards diskless type machines. But technically speaking, MinIO actually doesn't really notice the difference. You could just co-locate. If you have enough CPU cycles, why not? Smaller scale, HCI makes sense. Larger scale, disaggregated storage and compute architecture makes more sense.
So MinIO in that case is implemented as just like any other container microservices solution. It can run on any of the cluster nodes or workers that are available, assuming they've got storage.
Exactly.
Huh.
Yeah.
Maybe there is another question about multi-tenancy and its quality of service. I mean, yes, you can spread the volume across all the cluster, but actually after some time you need to segregate the performance because, as you said, you have developers and production in the same cluster. So a nice developer could run some really fancy queries, for example, on your object store and create some issues. So how are you limiting the developers, or is it in terms of number of instances of the MinIO nodes, or is it more about load balancing in the front end, or what?
In fact, like when Daniel goes through the provisioning of the demo, provisioning of the tenant, he will show you from the MinIO tenant. So there are two parts, right? One is the high availability SLA requirements. The other part is the QoS, very specific details of throttling the tenant. Now, in terms of a given tenant, I want this much capacity and I want this much high availability requirements. When you provision the tenant, it will tell you, okay, if you want this much usable space, it's a balance of, if you want more usable space, percentage of usable space to be higher, you will reduce the parity. If you reduce the parity, then it will also reduce the availability. So it will visually tell you as you play with, we want 4 node failure tolerance. Say the Seagate example I was giving, they have 16 racks and 7 out of those 16 racks can entirely disappear. You won't lose data or availabilities. 8 racks can disappear and you can still have read-only access to those 16 rack cluster. You can go to massive level of availability, but then you would lose the usable space because it will cut by 2 if you go that level, right? Now, that is easier part by controlling just the parity and capacity, how much you ask, that MinIO will determine what's the right ratio, and then your tenant gets spun up. But then the isolation, like given, what if I have, say, these 4 tenants simultaneously on the same machine? In fact, like in the cloud environment, 4 is probably a single customer only will have like so many of them. When you have lots of them, what happens is that you don't want a rogue application. Sometimes even unintentionally, there was a crash loop and then it just started consuming resources. You don't want the outage to spin out of control and affect everybody. How does that happen? That isolation, in fact, typically all the Kubernetes people, like their idea is, that's exactly why you should use C groups namespaces, the Kubernetes way of isolation. And the CSA layer also can control this in terms of how much disk space to use, how much IOPS to use. The advantage of solving this, the Kubernetes way means that I can apply one universal QoS policy, meaning the same style, same API mechanism across. This is an area I would still say Kubernetes is maturing. It's still not there as where VMs are, but like C groups and namespaces, particularly in terms of the isolation, both in terms of security and the level of QoS control, it's an area of improvement today.
Yeah. And here is also where leveraging Kubernetes, for example, if your CNI driver has support for traffic shaping, you can actually limit the bandwidth that an individual tenant is consuming. And you can actually make this based on the size of the tenant or the applications that you have, or you're running on top of Kubernetes. So it's something that Kubernetes is already bringing to the table, and you can just leverage to do this QoS prioritization.
Yeah, but Daniel's point actually was a good point that like almost that's what customers do. Instead of using C groups, namespaces type isolation, like throttling, they use the network bandwidth and IOPS throttling. That's easier, and that's what every customer does in terms of controlling the data traffic, and then you get the QoS effect anyway.
Great. Thank you, AB. Thank you, Daniel. All right, the last bit before we get to our demo is GUIs. So listen, we started the cloud native way. We did that with automation, with APIs. That primarily led us down the path of a command line interface. And we developed MC, which has been immensely popular in the business. As we started to do our integration with VMware, literally 18, 19 months ago, we started to see the value and the power of graphical user interfaces in really reaching across and expanding our audience. And so as we thought about engaging with that IT audience, we engaged in the journey of basically building a graphical user interface that had all the functionality that we had in our command line interface, but did so with just a handful of clicks. And so what Daniel's going to show you in the demo is the ability to provision multi-tenant object storage as a service, right? And do so basically with just a handful of clicks. You don't even have to know how to spell Kubernetes. And yet we've retained all of the deep functionality that is available to you through the command line interface. And so this is really important stuff as we think about what it is that we need to do to really grow the MinIO audience and make sure that we can reach across to IT and really build on this DevOps kind of cult following that we've already developed. So with that, why don't you take us through the demo, Daniel?
So I'm going to resume from where we take off, right? I previously showed I had 3 different cloud providers, and I was experiencing, I was expected to have a consistent experience on all these different 3 cloud providers. So on this part of the demo, what I'm actually going to show you is the infrastructure part, how I provision object storage to serve different business units, different teams, or different customers. And right off the bat here, I logged into my operator UI, and I have a list of tenants. So the tenant right now is an analogy that we used to describe a MinIO deployment. And the whole idea is that you can have them different configurations, different capacity. You can update them out of band. Perhaps you want to be updating one business unit at a time or one customer at a time, and make sure that upgrades are going as smoothly as expected. And that's the best part, that we are actually isolating and treating every tenant as its own deployment and not mashing them together into a single piece of software. So I think the best way to actually understand a tenant is actually creating one. So let's do that together now. So I'm going to hit create tenant here, and I'm going to start. So the first part is naming my tenant. Let's say I'll be creating some call center storage, right, for my US East region. And first I'll be selecting a Kubernetes namespace. This is where AB was going into the importance of the isolation of resources. We're leveraging the Kubernetes namespace for guaranteeing isolation between the tenants. This also lets you control different things such as storage type, resource quota. We were talking about the traffic shaping capabilities as well. So this is the first part of how I want to actually segregate my tenants, right? Isolate them. And I'm going to pick one of the storage classes. You can see I'm leveraging Kubernetes storage classes to actually select a type of storage that I want for my tenant. In this case, I have 3 types of storage: NVMe, SSDs, and hard disk drives. And perhaps for this type of recording, I want to go with something very deep. So I'll go with hard disk drives. If I were to go into my next step, right, that will be my sizing of my tenant. I will be answering questions such as how big do I want my tenant? And overall, the idea here is that it's all about the self-service. You can see that I'm actually provisioning everything, and we're trying to make it simple. We could have made it as simple as 2 steps. For you guys, we're going to take a small detour and show you all the things that you can configure, right? Things such as simple as whether I want to deploy a hardened image of MinIO or perhaps a previous version, or I'm using some private Docker registry. This is pretty common, right? So we probably on an air gap environment, you want to be able to use custom images. You can configure those. These are cloud environments, so I'm also actually asked if I want to expose this to the internet. Of course, I want to be this exposed to the internet as soon as it's ready, so I can start consuming object storage. On the next part, this is another part that we were talking, right? So how do I control the placement on this very large Kubernetes cluster? By default, we let the Kubernetes scheduler take care of it. But of course, you can take control of it and say, perhaps I want to do rack awareness, or I want you to only be deployed to a certain part of the cluster. And I'll be using some node selectors to make sure that my storage only lands on the type of nodes that I want. And now you can actually be managing a very large Kubernetes cluster and have both your compute applications as long as your storage application, in this case, MinIO, coexisting, but actually having them properly placed on the type of nodes that you want to do, right? So you no longer need to manage on a single cluster, different Kubernetes cluster. It could be just one cluster and just do node selectors, right? And the next part is, it's controlling the access. I previously established that even though I was using different cloud providers, I could be controlling all the access to a single sign-on type of solution. Right, so I actually show you OpenID for that case, but we also support Active Directory LDAP. And this is where you actually, as you're providing storage for new tenants, right? You could say, okay, I'll be enforcing either, I'll be using MinIO's built-in identity provider. I'll be configuring another single sign-on type of solution like the one I've been using.
Hey, Daniel, is this, is the MinIO cluster spanning multiple clouds in the on-prem that you created earlier? Is that?
I actually have a cluster per cloud provider, and I've set up replication. We're actually going to touch on that on the next part of the demo.
Okay.
But where I've actually made them behave like a single one.
Right, but they each have their own, effectively.
Yes.
All right, thanks.
So, but this is the part where, I was able to jump between all these different cloud providers and make it extremely simple because I had single sign-on, right? I didn't have to manage different set of credentials for different cloud providers. And then we also have support for Active Directory LDAP, which is a very popular enterprise identity management solution. So once we have set up how we're going to control the access, we can start talking about in terms of security. This is a communication type of security, right? By default, we manage all the certificates. You don't have to do a thing. We do everything inside the Kubernetes cluster. We're using its internal native certificate sign request. But of course, MinIO can also terminate TLS. You can bring the certificates to do all this setup. If you see, we're making it extremely simple, right, to configure all these things where, security is one of those things that no one really understands completely, especially TLS, right? It's so confusing. So we can either manage things automatically for you, or you can bring your own certificates. You can say, okay, don't manage certificates automatically. I'll bring every single certificate that you'll be needing. All of that is configured, right? And we need to establish a secure communication channel so that we can actually then switch the conversation to encryption at rest, right? So once you have a secure communication channel, it's the same. If I need encryption at rest, I can configure a KMS, right? So, and this is where you can, if you're working on on-premise deployments, you can bring your own KMS, set up a HashiCorp Vault, Gemalto type of solution. Or perhaps if you're running on any of the different cloud providers, we also support the cloud providers KMSs here, right? So, and again, we're trying to make it extremely simple, right? So if you need encryption at rest, we're even guiding you, like, for example, for HashiCorp Vault, you only need to configure 3 values, right? But if you're using AWS KMS or Gemalto, perhaps you'll need some extra configurations. But right now, you're not having to deal with any low-level configurations, creating configurations files, anything. We're just asking you the simple questions. We're just trying to get you online as quick as possible. And on the last part of this setup, I'm actually going to reach the sizing of the tenant again, right? This is the part that I skipped at the beginning. This could have been 2 steps, name it, and then size it. But then I'm back here and sizing it. And this is the part where I can actually tell the operator how big do I want my cluster to be. Let's say this is a 32 nodes setup that I'm doing, and I'll be provisioning 24 drives per server. And this is, let's say, 100 petabyte setup, right? So it's very large. I know I have all these machines. I have that large drives. I can also pick the erasure coding parity. The erasure coding is how MinIO protects the data. And the parity is actually how much parity data I want to protect my other data, right? So if this is not very clear what it does, we actually offer a preview of what's going to happen here. So you can see that for the 32 server setup that I'm planning on 24 drives, and the EC8, which is the largest parity value we support, out of the 100 raw petabytes of capacity that I'm provisioning, I'll be getting 50 usable petabytes of capacity. But then this will also give me a tolerance of 16 servers failing. In this case, this was related to pods in Kubernetes lingo, but that's a lot of server failures I can tolerate. And this is where Eddie was talking about, Seagate did this setup of 16 racks, and they can tolerate 7 racks failing altogether and still keep read capabilities. But if you're making this wide of a storage deployment, perhaps you want to go something, you can say, okay, perhaps I want to go more dense in terms of data. So I'll reduce the amount of parity. And this will actually give me more usable capacity. If you see, I went up from 50 petabytes to 75 petabytes. And I can still tolerate 8 servers failing on me. That's still pretty good. So this is so that you can also get an idea of what's the type of service level agreement that you can provide for your tenant, your customer, or the business units that you're provisioning object storage for.
So Daniel, that EC8 and EC4, is that, you mentioned it's server failures, but they could also potentially be drive failures within a server or something like that. And
that is
so
correct.
EC8 says I can tolerate up to 16 failures. And EC4
16 server failures. Right now I'm doing a very large 32 server setup, and then I'm actually putting 24 drives per server. But then this means that I can still tolerate a large number of drive failures, because and this will go actually into storage discussion where all these drives, we're actually going to organize them in different erasure sets. And then we'll be tolerating, if you go with the highest value EC8, we'll be able to tolerate up to 8 drive failures per erasure set. But in this setup, you'll have plenty of erasure sets. This means that per machine, I can still tolerate half the drives failing. Daniel,
if you show the online calculator, it actually tells the number of drive failure. Usually that's much higher. Drive failure tolerance is way higher than the node server. You can zoom in a little bit.
Yes.
Yeah.
So if I'm going with the 32 servers, 24 drives, and I was picking the EC8, I will still be able to tolerate 7 out of 16 drives per server failing, right? So, and then, but also this means that I can also lose 7 servers altogether, right? And still the data will still be in a writable state.
Okay, thanks.
Yeah, and this calculator, we have it on our website. You can actually come and play and see what is the expectancy from something that you're planning on building. So going back to the demo, the last part, I'm going to go to something that fits this cloud instance, because even cloud providers, they're afraid to give you that much capacity. So I get a review, and then I just hit create, and I get a reminder of the credentials that were generated for this tenant. I can back this information. And that's pretty much about it, right? So this actually, it's going to take a couple of minutes, and now I have a full-fledged object storage ready. So something I haven't actually showed you is what all the things that I can manage from inside a tenant, right? If I were to go into one of the tenants that I have here ready, I will be able to see important details about them. I can perform upgrades, right? I can look what's the state of the system, like in terms of metrics. This actually showcases our Prometheus integration. I can see what's going on in terms of activity, traffic, or resources, what's going on with my system. I can review security configurations, etc. Right? So if I want to update certificates, etc. But the whole idea is I'm getting this, and I know I can have the same solution available across all these different cloud providers. Right? There, even if this is on-premise deployment, it won't be different from how I'm actually managing the storage on Azure or on Google Cloud.
So effectively, you're creating these tenants across all 3 MinIO clusters because it's being replicated across all of them, so that tenant would be available in any of those environments. Is that how I read this?
Well, this is actually only available in one of the environments, right? But now I can actually go to any of my other cloud environments. Perhaps I can go to Azure and provision a different tenant. If I'm actually going to be doing some failover or some disaster recovery or some active replication, I will come and set up a tenant with the resources that that Azure is offering, right? They offer different storage classes, right? So perhaps on my on-premise deployment, I'm using NVMEs, but if I want to go to Azure, I have to use their Ultra drives. So then I can set up things that are similar, right? Or perhaps on Azure, I don't need that much capacity. Perhaps on premise, I'm doing my 100 petabyte deployment, but on Azure, I don't want to pay for 100 petabytes on Azure, on NVMEs, right? That might be too expensive. So I may actually set up something smaller. and set up either replication or tiering, which is another thing that we're going to touch up on the next demo.
Just Daniel, one point. So it's easy for us to just do, like, when you provision one tenant here, just all simultaneously provision tenant across other side too. It's the same YAML, right? You just have to tell that Kubernetes cluster apply this YAML. But the reason why we are not doing it like that is because almost always what happens, like the other site may not be a homogeneous hardware as this site. Sometimes customers also add the second site at a later stage, then or sometimes like it'll be like this site is local and that other site is on the public cloud. Because they are going to be heterogeneous, you can't have the same questions, like even the number of nodes and parity, like even the capacity. While the capacity is same, the number of nodes could differ. That there it could be more nodes, lesser drives per node, or it could be denser. MinIO allows heterogeneous clusters to be paired, and that was the reason that okay, you configure this cluster this way, that cluster that way, and then now you link them in the second step.
So typically replication requires an equivalent amount of server storage and all those other things in all locations that are being replicated. But in the case with MinIO, that's not required?
The capacity has to be same, obviously, right? Because otherwise we won't be able to keep all the data there. But the configuration of the cluster, there it could be more nodes and thinner drives, or denser servers. The parity thing, even there, maybe you didn't want to link both of them under same IDP or same key management server. You want that cluster. It could even be ARM based or AMD based. Because of it's almost all the time we find that they want to even replicate across heterogeneous clusters. But yes, you do need the capacity, usable capacity, to be same.
Okay, thanks.
Yeah. And I mean, on premise here, I actually have a larger cluster on premise, right? Our hardware is impressive. It's 100 gigabit Ethernet NVMe drives, and I actually have multiple terabytes at my disposal. So I can actually replicate my whole Google Cloud environment, my whole Azure environment to my on-premise deployment, right? So, and then have because my on-premise deployment is actually larger. It's the same size or even larger. And I can actually use it to back up multiple cloud deployments as well.
So let's summarize this section here, if we might. So listen, first off, Kubernetes native object storage equals MinIO. And even Enrico, who's on this call, has basically called us the best object store on the planet. He made us a leader in both of his excellent must-read radars that he put out, both the regular object storage radar and the high-performance object storage radar. We were the only vendor to earn that distinction. But I think the other thing, in addition to that, is that we've clearly invested an immense amount of time and effort into our Kubernetes chops, to our S3 chops, and to our object storage chops, because it's the only thing that we do. And so that makes us distinctive in this market. We also talked pretty much in great detail here about multi-tenancy versus multi-user and why multi-tenancy matters. We check every box there. It's a multifaceted type of problem, but from lightweight to isolated namespace, we're on every single one of those elements. And then finally, as you saw, a great graphical user interface can allow you to do amazing things. It can be a force multiplier for your entire organization. And so we still see, our cult DevOps following, looking at our GUIs and just loving what we're doing there, because it allows them to do things very, very quickly and to understand and allow them to educate the rest of the organization on exactly what it is that we're doing.